Okay, so how do you take a picture of something that's literally smaller than a wavelength of light? I mean, you can't, right? Well, you can. The answer is an electron microscope. But the way it works, it's a deep dive into some of the absolute weirdest corners of quantum physics. It really all boils down to a single, solitary electron, and how that one little particle can somehow map out an entire landscape of atoms, all by itself.
And this quote, this is really the heart of the whole puzzle. It says diffraction patterns are formed by, get this, individual electrons interfering with themselves. Just let that sink in for a second. How can a single thing interfere with itself? It makes no sense, right? It sounds completely impossible. But stick with me, because by the end of this, we're going to see exactly how that's not only possible, but it's the key to everything.
All right, first things first. We need to get a handle on just how lonely these electrons really are. Because inside what's called a transmission electron microscope, or TEM, each electron is basically on a solo mission. And that right there is the whole secret.
So, check out this number, 0.037 meters. What is that? That's about 1.5 inches. And in a typical electron microscope beam, that is the average distance between electrons. Think about what that means for a second. The microscope column itself isn't that long, so at any given instant, there is almost certainly only one single electron inside the entire machine. Just one.
So if they're that far apart, we're talking over 1 inch, there's no way they're bumping into each other or interacting in any way that could create an interference pattern. So that whole idea that maybe the electrons are interfering with each other? Nope, that's off the table. It's just not possible. The interference has to be coming from somewhere else.
And that brings us right to the main event, the big question. How on earth does one electron, flying solo, manage to map out an entire field of atoms? How does it create a complex picture? Well, the answer, it requires a pretty major shift in how we think. We have to stop picturing the electron as a tiny little ball and start picturing it as a wave.
Okay, this is where we get into the physics of it. The key concept is called the de Broglie phase lag. Now, I know, that sounds super technical, maybe a little intimidating, but the core idea is actually pretty straightforward. It's all about what happens to that electron wave when it passes through a piece of matter. Now, you've probably heard of something called quantum tunneling, right? That's where an electron hits a potential energy barrier, like a wall, and its wave kind of slows down and decays. Well, what's happening here is the exact opposite. In a microscope, the electron is actually attracted to the positive atomic nuclei, so it falls into a potential energy trough. And this is the part that blows my mind. Instead of slowing down, the electron's wave actually speeds up as it zips past the atom. Its wavelength shrinks. It's the complete opposite of what you'd intuitively think would happen. Okay, so this change in speed is what creates that de Broglie phase lag we were talking about. The best way to picture it is this. Imagine the electron's wavefront moving forward. The part of the wave that goes through an atom gets a little speed boost, so it gets ahead of the parts of the wave that are just traveling through empty space. And if it passes through a whole column of atoms, it gets an even bigger speed boost. So what you end up with is a wave that's now totally out of sync with itself. So by the time that single electron wave comes out the other side of the sample, it's basically carrying an invisible map, a phase map of the atomic landscape it just flew through. The information is all there, it's just encoded in these subtle shifts in the wave. The problem is, our detectors, well, they can't see phase. They can only see intensity, bright or dark. So how do we make this amazing invisible map visible?
Well, this is where the sheer genius of the microscope's design comes in. We have the map. Now we just need a clever trick to actually read it.
And the trick? It's called the Scherzer defocus, and it is so clever it's beautiful. What do? You deliberately throw the microscope's objective lens slightly out of focus. It sounds wrong, right? But by doing that, you give those different parts of the electron's own wave, the bits that got sped up and the bits that didn't, a little bit of distance to travel and overlap with each other. And when they do, they interfere. The parts of the wave that are now out of phase cancel each other out, creating a dark spot. And the parts that are still in phase add together, creating a bright spot. You've just converted that invisible phase map into a visible intensity map, a picture.
And just like that, there it is, the electron's own wave, interfering with itself, made visible by that clever little defocus trick, creates the final image. You get dark spots where the atoms are and bright spots where there's empty space. It is a direct photograph of the atomic structure.
So let's just recap. We went from a single lonely electron to a quantum wave to an invisible map to a clever optical trick. So what are the results? What can this incredible quantum camera actually show us?
Well, the images are just breathtaking.
So, what exactly does turning a quantum wave into a picture let us see?
I mean, we can see the atom-by-atom structure of materials. We can look at a carbon nanotube and literally count its 15 atomic layers, and even see how that tube is closed off on the inside. We can see individual columns of atoms in a crystal lattice. There's even potential to see things like the alpha helix structure in a hemoglobin molecule. And every single one of those images is built up one electron at a time, each one interfering only with itself.
And of course, this technology is not standing still. The push to see the fundamental building blocks of our universe with even more clarity, well, that never stops.
Yeah, today's state-of-the-art microscopes use what are called aberration correctors. Basically, they're incredibly sophisticated magnetic lenses that fix the tiny imperfections in the system. And what that does is push our resolution into the sub-angstrom level. We're talking about seeing details smaller than a hydrogen atom. It lets us image really light, delicate atoms like carbon without just blasting them to bits, which is, a total game changer for biology and materials science.
But even with all the incredible engineering, all the complex optics, and the powerful computers, it all comes back to that one single, beautifully strange quantum idea: a lonely electron behaving like a wave and interfering with itself. And really, that's the thought I want to leave you with. We took something that sounds like a total paradox, a piece of quantum weirdness, and we figured out how to turn it into a camera that can photograph individual atoms. It just makes you wonder, what else is out there hiding in plain sight within the strange rules of physics, just waiting for us to find it?